Hi guys, so this is the 3-4 lesson. It is called Implicit Differentiation. Okay, so basically everything that we've done so far with derivatives has been called explicit differentiation, which means basically everything that we've done has been y equals. Y is equal to x squared. Y is equal to x over the quantity of x minus 1. Okay, and so forth. So implicit differentiation basically allows us to solve or differentiate formulas that have an x and a y, not necessarily that are set equal to the y. Okay, so these are examples of equations that would require implicit differentiation. Okay, so the way that you go about doing implicit differentiation is basically you're just going to differentiate both of the sides with respect to x, and any time that you take the derivative of the y, you just simply add on the hook-on factor, which is the derivative of the y. Okay, so we can call that either the y derivative or dy dx. Just remember that these two things are the same exact meaning, just a different notation. So once you derive both the sides, then basically you end up solving for the dy dx piece. Okay, so a couple quick examples. These first couple examples are already set equal to y, so really you do not need implicit differentiation to do them. We can do it using implicit though. So for question number 1, if we derive both sides, you can say, well, what's the derivative of y? Derivative of y would be 1, and then you have to multiply by the hook-on factor, which becomes the y derivative. The derivative of x becomes 1. Okay, so that would be the derivative of that particular equation. For number 2, the derivative of y is derivative of y, and the derivative of x squared is 2x. Okay, so then number 3 gets slightly more complicated. This one has a quantity that's squared. You could FOIL this and then use the basic rule to differentiate it. Or you can use the chain rule, which we just learned, and that's the one I'm going to do. So we derive our y, and then the chain rule says we derive the outside, so 2 times 2x minus 1 to the first power times the derivative of the inside. So the derivative of the inside would be 2x. So you could technically leave it that way on a free response question. I always like to simplify though. So we have 2 times 2x, which makes 4x, and we're going to distribute the 4x into the quantity that's linear. So that becomes 8x squared minus 4x. Okay, so question number 4 is really the exact same question as number 3, but they write the function as f of x rather than as a quantity in itself. So I will use the chain rule here. So we have the derivative of y. Okay, so the chain rule is we derive the outside, so we have 2 times the f of x to the first power times the derivative of the f of x. Okay, so excuse me, that one cannot be rewritten. You would just call that good. Okay, now moving to question 5. Now this one does actually require implicit differentiation. You have x is equal to. Okay, so we're just going to derive each side individually. So if I derive the x, that would just become 1. The derivative of y squared is 2y, and then I have to multiply by the hook-on factor, so the derivative of the y. Okay, I don't want to leave it like that. Remember, finding the derivative, I have to set it equal to the y derivative piece. So I would divide by 2y here and say the y derivative is equal to 1 over 2y. Okay. So on example 1, they have another equation that does require implicit differentiation, and they ask us to find the y derivative. Okay, so I'm going to derive each term individually. So the derivative of x squared is 2x. The derivative of 2y cubed would become 6y squared times the y derivative. The derivative of 3x is 3. And the derivative of 6 is 0. Okay, so that is the derivative of the equation, and now I need to set it equal to the y derivative piece. So I'm going to subtract the 2x and subtract the 3 to the other side. So I have negative 6y squared times the y derivative is equal to negative 2x minus 3. Okay, so then I have to get rid of the negative 6y squared, so I'm going to divide by that. Okay, and in doing that, I notice on this now that everything is negative. I'm just going to divide everything by a negative 1. So everything will turn positive, so I'll get 2x plus 3 divided by 6y squared. Okay, so now that is the derivative, and it is set equal to the y derivative. Okay, moving on to question number 2. Now this one says to find the slopes of the lines that are tangent and normal to the graph. Okay, so it's asking me two different questions. It first wants me to find the slope of the tangent line, and then it wants me to find the slope of the normal line. So if you remember, the normal line is just simply the perpendicular slope to the tangent line. So again, we are going to derive this equation just like we did this one over here. So I'm going to derive each term. Derivative of x squared is 2x. The derivative of 4x squared is 8y squared is 8y. And derivative of 25 is y. Whoa, slow down there. You guys see what I missed? Times the y derivative is equal to 0. There we go. Okay, so now I want to set it equal to my y derivative, so I'm going to subtract the 2x to the other side. So I'm going to have 8y times the y derivative is equal to negative 2x, then divide by 8y. So the y derivative is equal to, let's see, we can reduce 2/8 by 2 and become negative 1/4, so there we go. All right, so now we have to use this point. Now notice that this time my derivative has an x and a y in it, and so does my point. So what I'm going to have to do here when I find the slope is I have to plug both the 3 and the 2 in to the x and the y values. Okay, so my 3 is the x, my 2 is the y. So when I plug this in, it'll be negative 3 over 4 times 2, which gives us negative 3/8. Okay. So right there, that is the slope of our tangent line. So I can say slope of the tangent is negative 3/8. Okay, and then we can find the slope of the normal line. Slope of the normal line is the negative reciprocal to that. So the negative reciprocal would be 8/3. Okay, not too bad. Okay, so now question number 3 says to find dy dx. Now remember, dy dx is just simply the same as the y derivative. It's just a different notation. Same thing, but we're going to use dy dx instead. Okay, but other than that, we're really doing the same as question number 2. We're evaluating at the point 1, 2. Okay, so I'm going to derive this function. So x cubed derivative would be 3x squared. Now notice on this term I have two things that are being multiplied. Okay, so the first thing I'm going to do is I'm going to pull the minus 2 off. And I'm going to treat this x and y as two quantities that are being multiplied. So to derive two quantities that are being multiplied, I have to do the product rule. Okay, so doing the product rule between x times y, my x is the first, the y is the second, so I have first d second. So the derivative of y would be 1, but I have to multiply by the y derivative, so dy dx, plus the second d first, and the derivative of x would just be 1. Okay, so I'm going to continue on deriving each of these terms, and I have plus 3y, or excuse me, plus y cubed, so that would be 3y squared dy dx. And the derivative of 5x would be 5. Okay, so at this point I know I'm trying to solve for dy dx. The first thing I have to do here is to distribute this negative 2 through. So I'm going to have 3x squared minus 2x dy dx minus 2y plus 3y squared dy dx. Okay, so then what I'm going to do is any term that does not have a dy dx on it, I'm going to send to the other side. So I'm going to subtract this 3x squared and add this 2y. So subtract the 3x squared, add the 2y. So I'm going to be left with negative 2x dy dx plus 3y squared dy dx. It's going to equal 5 minus 3x squared plus 2y. Okay, so now to pull the dy dx out as a single piece, we're going to pull it out like a greatest common factor. Okay, so we're going to pull it out, dy dx times, and if I pull that out of the first term, I'd be left with negative 2x. And the second term would have a 3y squared left over. Okay, the right-hand side, we're not doing anything to it, so it stays the same. Okay, and then our last step here is we need to get rid of this quantity, so since it's being multiplied, I'm going to divide by it. So I'm going to have dy dx is equal to 5 minus 3x squared plus 2y all over negative 2x plus 3y squared. Okay, so there is my derivative of the function, my dy dx. And so now what I'm going to evaluate it at the point 1, 2. I'm going to run out of space here. I'm going to use a different color. So I'm looking at dy dx at 1, 2. So I'm plugging in 1 into the x's and 2 into any y's I see. So x squared, so 1 squared plus 2 times y, which would be 2. And I have negative 2 times 1 plus 3 times 2 squared. Okay, so then I simplify that. So I have, let's see, on the top I have 5 minus 3, which is 2, and 2 plus 4 is 6. And then on the bottom I have negative 2 plus, let's see, this becomes 4 and 3. 4 times 3 is 12, so negative 2 plus 12 is 10. And that would reduce 2 by 2, so 3/5. Okay, so that would be the slope of the tangent line at the point 1, 2. Nice. Okay. All right, now question number 4. This one is actually probably quite complicated, and this will be a fun one. We're going to find the second derivative, and we have to do it in terms of y. Notice this notation right here says in terms of y. So that means we have to get rid of anything other than a y once we find the second derivative. Okay, so let's start with the first derivative. So the first derivative, I'm going to derive each term individually. So x squared is 2x. The derivative of y squared would be 2y times the y derivative. And derivative of 3 is 0. Okay, so I can't just stop and take the second derivative at that point. I have to set it equal to the y derivative before I do that. Okay, so I'm going to subtract the 2x, divide by 2y. So my y derivative is going to be, let's see, the 2's cancel, and I have negative y over x. No, I said that backwards. Negative x over y, excuse me. Okay, so that's the first derivative. Okay, and notice right now I have it in terms of x and y. Okay, so remember that, keep that in your mind. Okay, so moving down, we're going to take the second derivative. Okay, so we have the y derivative, the derivative of y is the second derivative. Okay, now on this other side, I have a fraction. Okay, so when I have a fraction, I have to do the quotient property. Okay, so I'm going to make sure that this negative stays upstairs with the x. Okay, so quotient property starts with the low. So ho d high, and the derivative of negative x would be negative 1 minus the high d ho. The derivative of y is 1, but I multiply by the y derivative all over the whole squared. Okay, so now this is quite interesting. I'm going to simplify this so that you can see what we've got. We've got negative y minus a negative, so plus xy over y squared. Okay, so right now I have this in terms of y's, x, and y derivative. Okay, so what I need to do is somehow manipulate this x and the y derivative. Do you see anything previous that we could replace the y derivative with? Okay, so hopefully you're looking at this piece right here and going, oh wait, we did do that. That's this right here. Okay, so we're going to plug negative x over y into the y derivative and replace it so that it would be in terms of, well, now we have an x and a y. We're getting closer. Negative x over y squared. Okay, now what I have here is a complex fraction. Okay, so this gets a little bit messy. So what I'm going to do is, really what I have is negative y, let's say minus x squared over y all over y squared. Okay, so I can just multiply this top and bottom by y over y, and it will come out eliminating this denominator. Okay, so watch what happens here. So if I multiply, so think of it like this, I'm distributing this through. Y times negative y is negative y squared. On the second term, well, I keep writing that as a plus, excuse me, minus. Okay, if I multiply this, x squared over y times y, the y's cancel and I'm left with x squared. On the bottom I have y squared times y is y cubed. Okay, so I'm getting closer. Now I have it in terms of y's and now an x. Right now what I see is that on the top, if you go back to the original, do you see the very original equation? See how close we are to that? X squared plus y squared is equal to 3. We have a negative and a negative. So what if we pull a negative out? We would have y squared plus x squared over our y cubed. Okay, and then at that point I now have that x squared plus y squared or y squared plus x squared is equal to 3. Okay, so I can replace that piece with 3. So I'm going to have negative 3 over y cubed. Okay, and at this point I am completely done. I have a derivative, a second derivative that is in terms of y only. There's no other variable involved. Okay, so your assignment, move this down a little bit. Okay, so I would like you to do, let's just kind of do a couple random ones here. Let's do 1, let's do 5, and let's do 9. Okay, so actually let's do these two. Boom. 1, 2, 3. Okay, so let's do 1, 2, 5, and 9. So those are your homework problems that will need to be done next time I see you.